All right. Well, thank you again, everyone, for being here on this Friday. We're excited to hear from two more speakers this week, and this is going to be our last in the Winter 2026 series. But very exciting to finish in the way that we are with Augusto Lima and Rachel Oien, who we'll hear from second today. So, Augusto is an early career researcher at the University of Bergen in Norway. He completed a master's degree in quaternary geology and paleoclimate at the University of Bergen, a bachelor's degree in geography at the University of Sao Paulo in Brazil. His research focuses on cryosphere dynamics with particular emphasis on mountain glacier systems during the late quaternary. His work integrates numerical modeling, remote sensing, geographic information systems, and AI-based tools, and he uses those to reconstruct glacier geometry and dynamics and has a strong emphasis on open science and interdisciplinary work. So we're glad to have you here today, Augusto. Please take it away.
Thank you for the nice introduction. And hello, everyone. So I'm going to showcase ongoing working that we have been doing the research group here in the University of Bergen. And the title is Mountain Glacier Evolution Since the Last Interglacial. So I'm going to show some insights we have been having through this year of working this new project. And this is a working collaboration with many co-authors, so it's not just me. So before starting to the work itself, I want to give a little background. So we are in the Mountains in Motion Research Group in the Department of Biology in Norway. And you may ask why these people from biology from Norway is coming to a conference in US to talk to us. So first of all, there we research present-day mountain biodiversity. But to know about the biodiversity nowadays, we need to go into biogeographical history of mountain ecosystems. And to reconstruct this biogeographical history, we need to understand the effects of glaciers shaping in the mountain ecosystems in the past. And to understand how glaciers have shaped mountain ecosystems, we need to reconstruct the glacier hypsometries across the glacier and interglacial cycles. And then in this part of glaciers and quaternary geology, I came in the group in the biology department. And last year, I gave a talk as well here in the 2025 winter series. And then I showcased the mountain glacier extents at the last glacial maximum. Is also part of this project I'm going to talk here. And Ben was one of the co-authors. So that's one of the reasons I was introduced with this group as well in the Western US. And now as well, have been working with Dr. Lee In-Ku in two, hopefully upcoming manuscripts. And maybe it's going to be Winter Speaker Series 2027. And now let's go to the work. So why are we researching mountain glacier evolution since the last interglacial? First, because it's important, we all know, is highly relevant to climate changes, to glacier modeling in the future, and so and so, but also is very important for, landscape evolution studies, for example, is very important to connectivity of alpine ecosystems, is very important to Paleolake studies, human migrations, and so and so. So we are also focusing this interdisciplinary alpine research here to give these modeling outputs long-term ones. And here, and otherwise, because like mountain glacier evolution since the last interglacial has been focused on steady state simulations so far, is centered at major climate events, and it's largely incomplete for few mountain ranges in the world. I don't know how to do the pink, is it like this one? No, anyway. So in many mountain ranges in the world is like quite incomplete. We have in some specific valleys, but the whole mountain range is mainly blank. And in other mountain ranges, it's completely unknown. So for example, in the northern Andes, there's no glacier reconstructions done by modeling. Yeah, and so far as well, mountain glacier evolution since the last glacial was a trade-off between simulated area. So if I have spatial resolution, simulation time, and ice dynamics complexity. So if I had a bigger area that I'm trying to model, I'm going to go to a very coarse spatial resolution. If I have a very complex ice dynamics, for example, full Stokes, 3D, and so on, I'm going maybe to simulate a very short time. If I have a very high resolution, maybe I'm going to have a 1D simulation or maybe a 2D simulation. So it's being a trade-off. So far has been very few studies that have been modeling long-term glacier evolution through large areas. And then here I'm going to show a little bit how are we doing it. So this is a very complex figure, and I'm going to focus in specific points here. So first we are using the instructed glacier model. It's a new AI-based glacier model. And for the ones that haven't heard about it, so instead of the solving CPU, numerically solving the ice dynamics at every time steps, the IGM is trained on other models. So instead of solving it, it's going to reproduce, and it's being trained and retrained along your own modeling. Yeah, and then for the SMB, we are only doing a PDD scheme. We are opting a simple one instead of a full energy model. And for our present day climatology, we are using Chelsea. And our paleoclimatology, we are forcing initially with EPCA, but because EPCA is from Antarctica, we are also compiling 102 regional proxies from different locations in our study areas. And also with this newly EPCA plus regional climate proxies, we are introducing a glacial index scheme from the precipitation. So it means when it's in the coldest temperature in our time series is going to have the most reduced precipitation. And then what are we doing? So we are reconstructed mountain glacier evolution since the last interglacial, but whoa, but I already said it in the title, so it's not that relevant now. But what we are doing with that, we are doing a three-dimensional modeling. We are using high order ice dynamics from Butler Patting. We are doing transient glacier simulations, not only steady state. And we are modeling 130,000 years to the past. And we are doing it in a 500 meters resolution in 4 different continents and 9 entire mountain ranges. And here we are having the Sierra Nevada in US. We are having Northern Andes, Central Andes, the Pyrenees and Alps and Caucasus in Europe. And in Asia, we are having the Ethiopian highlands, Eastern Rift Mountains, and the Ruizori Mountain. And then we are focusing on tropical zones and mid-latitude zones. So we are not considering the ice sheets or the Arctics. So we are simulating several mountain ranges at fine spatial resolution over full glacial interglacial cycles with high order ice dynamics. And now is something that we are doing it for the first time. So there is not other papers so far that have been reconstructing this long time series of transient simulations at that fine resolution through entire mountain ranges. Few papers do that, but it's more focused on landscape evolution dynamics with a simple glacier modeling, coupled to the landscape evolution model. And for that, we are using over 700 parameter calibration experiments, also only able because of the IGN. So if you are using previous like a PISM or other type of models, that type of experiments will take years to be accomplished. And we were able to do all that in 1 year so far. And now going a little bit into the methods, our multi-data comparison to validate or evaluate the accuracy of our model. For the last glacial maximum, we are using the mountain glacier extents at the last glacial maximum. So it's a database of published reconstructed glaciers from different authors. So we are using that to validate the LGM extent of our model. And for the present day, we are using two different data sets. For the extent, we are using the Randolph Glacier Inventory, the version 7. And we are also validating present day volume. And for that, we are using the data set from Farinot et al. And it's based on the Randolph Glacier Inventory as well. And then using these data sets, we are using a method called confusion matrix approach. So using our model output, we are calculating overestimated area, underestimated area. Overestimated is in yellowish, orange, and the underestimation is in red. And then we are calculating the correct presence of our model and the data compared. And we're also calculating the correct presence. So here I'm showing 4 different areas of our study because I don't have time to show all the different mountain ranges and areas. So I'm choosing the Sierra Nevada, the South Central Andes, the Pyrenees, and the Ruwenzori, one in each continent. And here we can see that the dynamics of our model changed a lot based on latitude and longitude. So we have like some models that are more sensitive to overestimation in the south, for example, in the Pyrenees. The same model have overestimation in the south, but underestimation in the north of the mountain range. In the Sierra Nevada, for example, we have overestimation in the northern, underestimation in the northern sector of the mountain, and in the southern section is mainly overestimation. But in the present day, it changed a lot, and we saw that so far our model doesn't work so well to estimate small scattered ice bodies, most likely because of the 500 meters resolution of our model. We haven't tried so far to go in lower resolution to see if this problem of small scattered ice bodies could be solved at reducing the resolution. And unfortunately, in the Sierra Nevada in the US, we were not able to estimate the present-day glaciers because they are very small and very scattered across the mountain range. And with the confusion matrix, we apply another method called critical success index that is basically calculate the presence, correct presence by the sum of correct presence, underestimation, and overestimation. So we get a percentage of how accurate our model were in comparison to the validation data sets we use. And then we ranked our simulations. So here, if you see in the image, each blocks is the compilation of all parameter calibration experiments we did. So for each blocks plot, we could have from 27 to 100 different simulations. So it's difference in between each simulated area. And then we think each block box with a symbol that I'm going to call here, we rank it. So we have simulation number 1, 2, 3, 4, based on the critical success index. And then we also rank it later on the success in each of our mountain range. So the block box here are showing the all assembled simulations, where we have the top simulations and the bottom simulation. And then the block spot area, the rectangle, is the average of the simulations. You see like in the rectangle, one black line. So that is like the mean value of each assemble. And then based on that, we decided to evaluate our model by ice cover frequency. So we are not going to select one best fit simulation here, but we are going to show how our different parameter calibration simulations show the frequency of ice cover in our models. And then keeping going on the critical success index, it showed lower model accuracy in the present day, as we showed before in the over and under estimation of the matrix. And then on average, our present day model outputs had a critical success index of 21%. Meanwhile, our LGM had a critical success index of 48%. Unfortunately, so far, all our present day glaciers is below 40% of a critical success index, but the Ecuadorian coordinators, here we got the best simulation here got a critical success index of 50%. And only 3 simulations at the LGM is below 40%. Meanwhile, 9 simulations through the LGM is above 50%. And analyzing our outputs, we saw that the glacier size does not explain performance because we have small glaciers like the Ruwenzori and the Sieme mountains. Both are small, but one has a very low CSI and the other has a quite high CSI score. And we also have bigger glaciers scoring low, like the Western and Central Cordilleras in the Northern Andes, or quite high, as in the Pyrenees in Europe. However, we saw that the problem is when the glaciers started to fragment in smaller ice caps or valley glaciers, as in the case that we see here in Sierra Nevada. So when it started in the northern section to the glacier body itself, it started to break into small ice caps. Our model was not well performing. And isn't the same in the Pyrenees here, when the glacier was forming different smaller ice caps apart from the main ice body, our model also didn't perform that well. And with that, we also perform a benchmark evaluation. So we got a few other papers that are already published in the literature, and we apply the same model data comparison methodology we are using here. And I'm showing 3 papers here. So for example, in the European Alps, we have one paper that scores 71%. In the Andes, we had another paper that scored 35%. And in the Himalayas, we had another paper that scored 42%. So with this benchmark evaluation, we are considering in our study so far that model reconstructions that are above 50%, they have a good agreement. That in between 40 and 50%, they had moderate agreements, and below 40%, we are having a bad agreements. And now I'm going to show the nice results that we have been doing. So first, I'm going to explain a little bit what I said before about about we are not evaluating the best fit of the model output, but we are evaluating the ice cover frequency. So in this image that we have the A on the top on the Bolivian Andes, we are going to see that in light blue is the area where 75% or more of our model simulated outputs simulated ice. So this area in light blue is present in 75% or more for model outputs. And then if you go down to the just blue here, we see that this area is only present below 75%, but above 25% of our model outputs. And the dark blue area is regions that are only present below 25% of our model outputs. So here we're analyzing how the glacier is sensitive to parameters choice and how parameters choice can originate different geometries or different glacier areas. And the parameters that we have chose to differ in between experiments was precipitation adjustment, the DDF, so the degree day factors or math factors, and also the sliding coefficient. So we are varying these 3 parameters here. And here we can see our simulation of the Bolivian Andes. And for that, we can see here that 85% of this glacier is representing 75% of our simulations. So this Bolivian Andes Glacier has low sensitivities, at least to our parameters. And also our parameters did influence the formation of the valley glaciers. So the black line is our validation data set that we used. And another important information that we saw here is that through the whole 130,000 years of our simulation, this area didn't reach present day level since the last interglacial. So the present day glacier geometry that we have now hasn't been seen through the whole last glacial cycle. And the algemic conditions that we saw here was quite sturdy from 20,000 and 800,000 years ago to 19,400,000 years ago. So LGM climate conditions dure quite long in this area here. Yeah, and then our second range that I'm showing is the Ruwenzori Mountains. And again, this area showed low sensitivity to our parameters. So 8% of glacier area was modeled above 75% of our simulations. Here we can see a little bit of difference from the Bolivian Andes, although it's also low sensitivity to parameters. The parameters here is quite important to model glacier valleys. So we see that when we change our parameters, the geometry of the valley glaciers in the Ruwenzori Mountain also changes. And as the Bolivian Andes as well, these mountain range haven't reached present day glacier levels since the last interglacial, and the LGM climate conditions was also stable. So we can see in the graph that it grew from 29,500 years before to 20,800 years before. So around 9,000 years in total. Yeah, and then the Pyrenees we start to see a little different history from the other mountain ranges. Here, the glaciers sensitivity is a little bit high in the valley glaciers. So out of the total area of glacier, above 75% of our simulation was 84%. So it's still quite stable in the main glacier body. But the valley glacier differs a lot in geometry and extent based on the parameters used. Different from the other two mountain ranges that I showed here, glacier size reached present day levels in 4 different occasions. So first one was around 108,000 years ago. I think the second one was around 96,000 years ago, and again at 84,000 years ago, and later at 16,000 years ago by our model. And the LGM conditions was quite short here, around 3,000 years in total, compared to the other mountain ranges that are more durable and stable. And finally, the Sierra Nevada in the US. This was one of the most sensitive areas to parameters. So only 62% of glacier areas was showed in 75 or above of our glacier model outputs. So it's very sensitive to parameters choice in our models, especially in the formation of valley glaciers, but also in the main body of the glacier here. And we can see that the northern section of the glacier was not so captured by our model. So probably it's sensitive to other parameters that we didn't vary so far in our simulations. And another interesting point in the Sierra Nevada is that it has been the glaciers that have reached present day conditions in 1, 2, 3, 4, 5 different occasions. So it's one area that have been glaciated and deglaciated multiple times through the last interglacial. And the LGM conditions in this area was the shortest of our simulations. So it was around only 2,000 years that the glaciers presented conditions similar to the LGM here. Yeah, so a little summary of the presentation. We are getting to the end. So we are showing the first high resolution model that used translate simulations of mountain glaciers for 130,000 years ago across 9 entire mountain ranges worldwide. We evaluated our model is a model data agreement with geomorphological reconstructions using glacier mountains and modern glacier datasets, the RGI and the Farinot. Our model show high agreement in 9 simulation domains within our mountain range, moderate agreement in 5 of our simulation domains, and low agreement in 3 of simulation domains at the LGM. However, our model show mainly low present day agreement. And then here we chose to evaluate glaciers based on the occurrence and frequency of ice across our ensemble instead of choosing a best fit simulation. Yeah, I think that's my talk, and I think I finished quite on time. Thank you for listening, and I'm open to questions. How can I finish? Okay. No.
All right. Thanks so much.
Thank you.
Augusto. We have time for maybe 1 or 2 questions.
If I understood, it looked like you said that 17 to 16,000 year stagnation period, was that documented in most of your locations that you were highlighting? 17 to 15 stagnation or regrowth?
You mean like when I say like when a mountain range showed a stable LGM period?
Yeah, just that one little blip after the LGM at 22, before 15.
I think I can share again. Let's see.
Just on your time.
Here?
Let me see. I can't see the bottom graph.
Can you see now?
Yeah, that one little blip right there after the 20. Yeah, right there.
Yeah, so we are using EPCA to simulate the paleo forcing. So all our simulations is forced by EPCA, but then we used regional climate proxies to differ how much was the temperature cooling, because EPCA is going to say, for example, that the LGM, the temperature cooling was minus 9.5, but then we changed it to temperature cooling based on different climate proxies at the LGM. But as we are using only EPCA to derive the paleoclimate temperature, the curve have some sort of stability through all our different simulations.
Okay. All right. Thank you.
Okay.
I've got a question. You mentioned that your model doesn't deal with the fragmentation of the smaller bits well. How are you trying to address that, and how much do you think it makes a difference in your sort of modeling of the reconstructions?
Yeah, so we told you how to address that. So one option would be to reduce the resolution, and we could see how it is going to work in simulating these small fragmented areas. However, to reduce the resolution, you would have to perform all the models again. Would take a few months to be finished. And the other way to use is to see different validation data sets, so different model data comparisons, because here we are based on geomorphological reconstructed glaciers. So we are not using directly moraines or other geomorphological filters. So our model data set also has a bias, right? The validation data set that we're using, because it's an interpretation of geomorphological features. And we can see this bias in different parts here, if I can show. Oh. Yeah, here. Oh. So if you can see, for example, in the South Central Andes, we have a big blob that is red, and it's from our validation data set that it shows this big blob as being a glacier area, but it doesn't seem coherent that a glacier would be here. So actually improving the validation data sets that we use could also improve the outputs that we see in the model. Or could also show that our model is a way worse than, but we had to see of different types of validation data sets, how it could change our outputs.
Thanks.
Welcome.
Hi, August. Maybe I ask a quick question for you to consider. I think it's really surprised me that the present-day glacier have a lower, accuracy. So based on my understanding, I think a lot of IGM work, they really kind of calibrate for the modern glaciers, for example, the European Alps. So, that may be related to some kind of mass balance or kind of, resolution definitely play a role. I think that's really kind of surprising for me for that. Mhm.
Yeah, we also got surprised by that, but in the end, is also a very interesting result to see that if we validate our model just in one time step, it doesn't mean that our model is good in all time steps, right? Because often we see that we simulate a longer time, and we're validating only one in one specific time, for example, LGM, and we have these moraines at specific times, and we use that to validate, and we say, yeah, our model is good. But with our model that we have been so far is that if our model is good at the LGM, doesn't mean it's good at the present day. And if our model is good at present day, doesn't mean if it's good at the LGM or in any other period in time. And another thing that we also thought interesting is that when people validate model, normally we don't have that many geomorphological features to be valid to work with on the validation, right? So it's quite restricted. So if you have a set of moraines in a few valleys, and based on that, we can say, okay, based on these 5, 6 different moraines, our model is good. But what we are seeing here is that the accuracy of the model varies a lot in space. So it can be very good in the northern section or northern moraines of a range. But if you go to the southern moraines or the southern section of the glacier, maybe it's not good. So it's, yeah, we're still like going through to see how to approach these results we are seeing. But I think it's quite interesting to see how validation plays a big role and how can we improve on that.
Yeah, thank you very much.
All right. Thank you again,
Yeah, thank
Augusto.
you.
It was really great to see the results of this very impressive modeling effort. You're really covering a lot
Thank
of
you.
interesting areas. So it is time to move on to our second speaker, Rachel Oien. Rachel, can you share your screen?
Yes.
All right, great. So Rachel is an honorary research fellow in physical geography at Durham University. She completed her PhD in geography at the University of Aberdeen in the UK and a master's in geology at the University of Illinois Urbana-Champaign. And she did a bachelor's in geology at Gustavus Adolphus College in Minnesota. Her research focuses on glacial geomorphology and quaternary paleoclimate, particularly how and when glacial cirques form, how long they take to develop, and what they reveal about past climate conditions. Her work includes studies of cirque development in Scandinavia, the Putorana Plateau in central Siberia, as well as her research on glacier change in Arctic Canada and Greenland. Sounds great. Go ahead, Rachel.
Wonderful. So My talk will actually follow nicely along from Augusto, so I'm glad I went second. But I'm going to be covering peripheral glaciers of Scandinavia and Greenland and rethinking about the terrestrial margins. So ice sheet margins matter, as we know, because they are the location of major outlet glaciers and ice streams. But they're also this area where we see the most rapid change occur in the terrestrial environment. As we heard in our last talk, as ice sheets decay and retreat, they become more fragmented. And this detachment process is important because as the smaller bodies of ice of peripheral glaciers, they respond faster to climate change than the main ice sheet because they are smaller. Now, right now in Greenland, they only occupy about 4% of Greenland's total ice area. But these ice bodies also account for almost 11% of Greenland's total ice loss. So, relative to their size in the peripheral area, they are contributing a disproportionately large amount. In the last decade, these peripheral glaciers and ice caps have lost almost 20% of their entire mass, which has equated to about 40 gigatons. And the rates are increasing. And so, as this margin becomes more fragmented, we also have an increase in peripheral glaciers. So, we're gaining more of them as they're becoming smaller. And this peripheral glacier margin matters because they are so sensitive to climate change. And as Augusto mentioned just a little bit ago, this detachment process and ice mass loss is often overlooked in models, particularly in ice sheet models. So as maybe an big ice cap becomes attached, is that mass actually lost? How is it counted? And how does that be taken into account on the paleo scale, the historical scale, and the modern scale? So really diving into these peripheral glaciers is important for understanding reconstructions and ice sheet evolution long term. So this peripheral glacier problem in the most basic sense breaks down into 3 time sets. We have a full ice sheet condition that then through retreat turns into these areas of outlet glaciers and these detached larger bodies of ice or mid bodies of ice. And then you may have the retreat of that outlet glacier, but do those peripheral glaciers hang on? And if so, how long? And because they are sensitive to climate change, what are they representing when they become topographically and hydrologically detached from this edge? So once they become this independent system, how do we equate for that mass change in our mass balance models? So right now, we're sort of misestimating ice sheet mass balance through time, and they're left out of a lot of the paleoclimatic reconstructions over time. So my goal is to look at this as a holistic perspective of how this has changed in the sort of peripheral sense and how it's changing in the modern context. And I'm going to be touching on both of those today. When I'm speaking about peripheral glaciers, I think of it as a continuum of climate sensitivity. So the smallest ones are cirques, our little glaciers. We have more mid-size and ice caps, and they are all shaped by climatic conditions and topographic restrictions. Today, I'm going to be addressing these twofold problems, looking at cirques from 2 different study sites. So to remind everyone, even though I know that the talks this spring have been cirque heavy, these cirques are these small confined glaciers, and they have a connection to their equilibrium line altitude, which is that point of net zero in mass balance between the zone of accumulation, which are inputs, and the zone of ablation, which are the outputs. And these ELAs can be easily reconstructed, and they provide an important connection to paleoclimate reconstructions. So in the most historical sense in Scandinavia, when we think about the Scandinavian ice sheet, this is the classic viewpoint that most people have in their minds. And these reconstructions are fantastic. We've got a maximum, minimum, and most credible. And a ton of work has gone into this. I'm not discounting that. But the issue comes into play when you start including peripheral glaciers. So in Scandinavia, peripheral glaciers are the smallest ones, can be easily mapped through their moraines and topography. A few years ago, I mapped 4,497 paleocirques. So these are cirques that do not have any ice in them in present day. There's another 500 of those, but these are entirely empty. That exist across Scandinavia. And if you direct your view to the red box on the map of the isochrons of the screen, you're going to see a huge mass of these dots, which we are going to get into. Each one of these points is a location of one of these peripheral glaciers that would have existed at some point. And the reason I count them all as peripheral glaciers is because this was all covered by an ice sheet at one point, and at another time, it was all something smaller. So if we zoom in on this area, we can see that this is the area of the Lofoten Islands. They were covered by the ice sheet during the maximum glacial extent at 22,000 years here. And as the really well-dated isochrons by Hughes et al. And Struiven et al. Monitored the deglaciation, they then become uncovered. So by the Younger Jurassic since the entire Lofoten Islands here, which is this area, become uncovered. And this is important because when we're thinking about their development, this area of Scandinavia would have been covered and uncovered by an ice sheet, but it wasn't inundated during the Younger Dryas. It stayed in the peripheral contents. The Younger Dryas margin came right up to about here, and they were not recovered by an ice sheet. So these cirques that exist there, like I said, it's a subset of about 4,500 across all of Scandinavia, but in these 2 degrees of latitude, we have about 1,700 cirques. And when you start breaking those cirques down into subcategories, 900 of them lie below 500 meters of elevation above sea level, and they exist outside the Younger Dryas limit. So you can see the amount of them, and we have the Younger Dryas extent highlighted here in lime green. So the Scandinavian ice sheet retreated back to this purple line, re-advanced to the green, and then back to the yellow. And so a lot of these features were not recovered. Now these cirques are, when you just look at the geomorphology using tools like ACME2, they are geomorphologically distinct. They have steeper head walls, more circular planforms, and are consistent with more reactivation or more modification in their cirque form. They also have a slightly different aspect. So what you're seeing here are cirques that have remained uncovered by the ice sheet and were not re-advanced. They have a mean vector of about 39. And cirques that remained covered throughout the Younger Dryas have a mean vector of about 23 degrees. And when we just break down the statistics of this, we have on the top here, these are cirques which remained covered by the Younger Dryas ice sheet, and the cirques down here were exposed during the Younger Dryas. And we can see that their relationship to their morphometry is different. And so we once again see these steep cirques that are more angular when they existed in the peripheral glacier system. This relationship repeats itself with slopes. So once again, we have steeper slopes or steeper head walls the older the cirque is, or the more time it's existed outside of ice sheet cover. And we see that this as a fairly strong relationship. Same with length, width, and perimeter. All of the cirques that have been exposed longer outside of that younger dryas margin in the periphery are better developed. But you don't have to just take my word for it. So I have some great footage to show you here. So last summer, I was privileged to be able to go to the area of Lofoten for 2 weeks with a team from Edinburgh and Aberdeen. And we were investigating these cirques via their moraines. And we used two methods, both Schmidt-Hammer and cosmogenic. We don't have the cosmogenic data yet, but we do have very consistent Schmidt-Hammer dates. And most of them I'll bring your attention to are this red box. And so most of our Schmidt-Hammer dates are coming back as pre-boreal, which is about 8,000 to 10,000 years ago. I'll see if we can convince it in some fieldwork photos. So some of what these peripheral glacier margins look like is in the bottom left-hand corner, we have the geomorphic mapping done by the Norwegian Geological Survey. Then in the upper left-hand corner, we have the LiDAR, where you can see these distinct moraines, and they have both their elevation and their Schmidt-Hammer value described on them, and then we have the drone footage. So these are large, well-developed moraines coming off of the system here. And from this last indication, we can see them coming down, and we have multiple advanced extents of these nested moraines, which have a Schmidt-Hammer relative age dating of pre-boreal. We have another example in Mortadellen. So this is an area just further south of the previous moraines. Once again, it has a Schmidt-Hammer age in that pre-boreal value. But I'd also like you to take note that what they have mapped here are De Geer moraines, which is an outlet glacier that would have had to exist prior to the readvance of this little glacier. Finally, this is an area of prolific De Geer moraines. De Geer moraines are this sort of repeating pattern that's known to be connected to outlet glaciers here, and they're coming up on the LiDAR, and they're mapped once again in the dark green by the Norwegian Geological Survey. If we zoom in to these areas of mountain glaciers here, or small peripherals, we have repeat advances that have come down and readvanced on top of this De Geer moraine. So these would have had to have occurred after the retreat of the ice sheet with this glacial readvance. And this is what it looks like in real life. So you can see those two readvances on the right overlaying the De Geers that step up this valley. And one of our last examples here is looking at the classic hanging valley. Does this repeat itself when we add in a little bit more elevation? Now, these are still under that 500-meter threshold, but in this scenario, we had 4 to 5 different advances, the most notable up valley, and some larger ones down near the ocean front. The moraine, which is furthest or closest to the coast at 31 meters of sea level elevation, actually came back with a value of about 31 for its relative dating, which would indicate that it could be younger Dryas in age. And our final moraine that we looked at, this is further south in Scandinavia of our examples, had a very extensive moraine, but we also wanted to investigate where there are other recessional moraines in this lake. So we've developed this little boat that goes out and maps the bathymetry to look at these investigations. So no longer will water be in the way in actually developing these reconstructions. And you can see that we've been able to fill in our topography here, which is great And once again, we have a pre-boreal Schmidt-Hammer age for this map. So what does this look like all together here? We took 21 cosmogenic samples that we're waiting on and did moraines from Schmidt-Hammer across 22 moraines. Those are in the yellow dots in the video on the right. So we're proposing that as the Scandinavian ice sheet retreated, these then became active glacier systems that potentially existed into the pre-boreal age, which would be either reactivation giving us indications of Holocene glacial dynamics, or maybe the Schmidt-Hammer is a little bit off and these are a bit older, but it would still help with the reconstructions of peripheral glaciers from the older and younger glaciers. So that's what it looks like in the paleo perspective. But now let's connect this to modern day. So I twofold am also thinking about how does this research translate into our present day issues of how we view the Greenland ice sheet. And I, a few years ago, did a postdoc with the University at Buffalo, New York, with Sophie Novicki. And what that was working on the Little Ice Age extent. And this was meant to be bridging this gap between where paleoglacier modeling could end and modern modeling would start. And it was this sort of connection zone of last resilience. And we ended up developing some masks that are usable, and it's gone on to inform Jonathan Karavic's work, which is looking at the peripheral glacier environment since the Little Ice Age. So in that paper, we quantified how much change there was in present, but this was all of the peripheral glaciers that weren't part of the ice sheet. And then we have the ice sheet. But what happens to that sort of mid group in the middle when it detaches, particularly in the historical environment? So I've also been working with an IGS working group on the delineation of ice sheets basins because I'm so plagued by this problem. And these are two examples of the initial results from this working group of the discrepancies of ice sheet mass in Greenland. So we have everything from the RGI, which are noted in red, to the different ice mass like bed machine, prom ice, GIP, RACMO, that are used in modeling, but there are such discrepancies in this peripheral glacier environment. It really makes sense that we still have so much error and guesstimations in what's happening in this environment. Do we count it as peripheral if it is detached now but was attached in 1920? How do we deal with that mass loss? Because if we just remove it, then it looks like a ton of mass has been lost, but it still exists if the maybe ice cap is still exists. It's just not part of the main ice sheet. So how do we really quantify this? Once again, I turned to the paleo environment because that is where I am most comfortable. And I started thinking about the peripheral glacier detachment in the sort of central western belt of Disco Bay and Disco Island. So hopefully you know that this is Disco Island here. Some of this work is being able because we've had an increase in the better isochrones of the major ice sheets. So this work was done by Tonk-Leger when he was at the University of Sheffield, and fantastic in the collation of the larger geomorphic features and isochrones, once again with minimum and maximums. But I'm always interested in the little bit, so I dove into this bit of research by mapping 527 cirques using ACME to dive into their cirque morphometry to look at the relationship of exposure age or time outside of the Greenland ice sheet to see if we have the same patterns versus, well, the ones that are still exposed. And I will say that these, if you're looking west to east, these graphs should be flipped. So the oldest cirques of exposure are out here, and they're at very low elevations, once again, below 300 meters. And we have this sort of humped age, cirque floor altitude environment. But we also see the same relationship that we saw in Scandinavia, where the cirques, which exist and have existed out of the ice sheet the longest, have the highest head walls. But what does this look like as we think about it? This is a cirque that has been exposed for and not recovered by the ice sheet since about 14,000 years ago. And then this is a cirque that exists right up close to the ice sheet, both in this peripheral environment. And they have this very distinct morphometry. So maybe the peripheral environment can be investigated through these very small bits of ice. So as we're thinking about this peripheral glacier environment, Greenland is going to continue to retreat. Its margin is going to continue to be dominated by smaller glaciers and ice caps, which respond differently in this sort of same system. As it becomes more terrestrial based, we're going to have more terrestrial glaciers which fragment. This margin is rich, but we really don't have a handle on this fragmentation that's occurring. So I think that it needs to be looked at from both the modern perspective, the historical, and the paleo perspective. The modern groups really look at how this impacts modeling, but we don't have a constraint on how this is viewed in the paleo environment. So I think that these peripheral glaciers are just this critical key point that we don't have much constraint on from both past and future. Scandinavia can be used for this proximity and to show how this fragmentation occurred in that paleo perspective because of the richness of the data. And Greenland is showing the same process right now. And these are just some fun field photos that we had in Lofoten. Thank you. I'll stop sharing.
All right, great. Beautiful maps and imagery, Rachel. Thank you for sharing that.
I was going to comment too. I really loved the embedded videos. It really felt like I was there. I'd love to know how you did that.
Sure. So we took drone footage up, and there, I mean, I will say that thank you to my two colleagues that we did long days, but luckily the sun was at about its peak of 24-hour days. So we did long days because these were only 6 of the 22 moraines that we did in about 12 days. So it was quite a bit, but yep, it was just drone footage, and then we used a software called Clip Clamp, which is free, and you can really edit videos quite easily as a novice in there and embed them in.
Can I
Cool.
chime in with a question?
Go ahead, Keith.
So I'm assuming when you're looking at cirque morphology, bedrock isn't an issue. That is, differences in bedrock is not an issue. But one of the things I was thinking about is, doesn't it make sense that if in fact you have an ice sheet overriding what is or becomes a cirque, there would be maybe less erosion that's concentrated in that area, as opposed to the flow lines, the one envisions in a cirque glacier, actively excavating. Do you see what I'm getting at there?
Oh, absolutely. I think that this is I've been privileged to work with Ian Evans at Durham, who we revere around here as kind of the father of cirques, and we have a lot of conversations of the twofold of how do you get a cirque and how much is it changed? So is it just the fact that you have this sort of frozen ice of the really cold ice sheet that doesn't modify it, and it's just a time-dependent feature? But then people use a feature to reconstruct a paleoclimate. So I think it's what is it really representing? Is it we know that they're cumulative, but what are those cumulative conditions? So I think that there could be some modification, albeit limited, on these cirques from the bottom of the ice sheet in the subglacial processes. But is it just a factor of reactivation time of the right conditions? I don't know if that answers your question.
No, it's fine.
Can I ask a question? I don't know if we're raising hands for this, but thank you, Rachel. Really, really cool talk. A lot of great visuals. I was actually curious about some of those images that you showed of the Daguerre moraines and how they're being overprinted by, I guess, another set of moraines from side valleys. And it made me think, I'm sure you've thought about this, but so since the Daguerre moraines are subaqueously deposited and presumably the other moraines that are overprinting them are not, can you use with the age control you have, are you able to use some of that information to help reconstruct relative sea level changes in these field sites?
Sorry. Maybe. So I will say that what's interesting about this particular valley in the area is that the Norwegian Geological Survey, you can't see any of it here, but has mapped all of this above the marine limit. Which calls into question, how do you have a series of Daguerre moraines if these are all above the marine limit? And just for context, isostatic adjustment in this area is about 10 to 15 meters. It's very small. We're basically at one of the hinge points. So it's almost negligible. We are waiting for dates back on Daguerres from right here, and then of course these moraines which have then clearly come at a later date. With relative sea level, I think it calls into question this area a bit, because if we're having Daguerre moraines and it's only been 10 meters of adjustment, I do think you'd be able to add that into the conversation, because there's Daguerres all the way up this side and out into the other fjord that it connects to. So we haven't entirely thought about that, but we are assuming that, I mean, it would have had to have been a little bit of uplift with this re-advance, because there's no indication that these were interacting with water.
Yeah, okay. I mean, it would certainly seem that you're below the marine limit, at least during the time of Daguerre moraine placement, right? And then if that's the case, I don't know if you're trying to use Cosmo to date them, then you're dealing with a complex exposure history. So
yes, we're doing Cosmo right now for the smaller moraines, the peripheral glacier moraines, but we haven't set in the Daguerre moraines yet, because it's a question of what sort of method that we would do with it. But we basically collected all the samples we could while we were there.
Great. All right. Well, thank you again.
Cal?
Yeah, hey, great talk. Thank you. And I was just going to clarify what Keith was saying. Keith, were you getting at like at LGM at full or at any full glacial maximum, you're pushing ice, you're removing nick points down the glaciofluve, where with glacial recession during any given glacial episode, you start more concentrating plucking into the cirque head wall region. So with full glacial maximum, you're actually removing nick points, just like a fluvial system removing nick points at maximum capacity of flow and then backfilling during recessive flows. Is that what you were getting at? I was just trying to understand your question, because that's a concept that I've been reading about, going back and looking at some of Mathis and Hobbs' turn of the century work on process from full glacial maximum to the end of a glacial episode. And Cotton and some of those early researchers. I'm just curious if that's where you were going with that.
Me?
Yeah.
I have no idea where I'm going. I'm old enough now that I can use that as an excuse. No, essentially what I was thinking is that when you have essentially an isolated cirque glacier, that the erosion might be more effective in a sense locally, right? And so then wouldn't be surprising that, when you have just cirque glaciation, that you're going to evacuate, erode, deepen, increase the head wall, presumably, right? Then if you had full glacial condition, that is with an ice sheet, you're just kind of overriding the landscape. And I don't know, of course, the cold base idea is also important there as well. But anyway.
No, it's interesting. Yeah. What do you have any thoughts?
I was going to say, I agree with you. I think what is unique about these is that they would have been reactivated for a short time. And I think that time coincides with when you have a sort of large ice sheet in the area. And then when the ice sheet ultimately recedes out of that younger Dryas advance, all of the glaciers meet their demise. So it's this sort of give and take relationship where they're uncovered long enough to become very active and leave this big geomorphic imprint and maybe hang on a little bit. But the minute you really lose that ice sheet, they're just gone. And it's something that could be a lesson for Greenland. So I think it's that twofold where you need them to be uncovered to be, yeah.
Got it.
Yeah, no, I see what you're saying. No, I like that concept. That's good. Thank you.
Yes. It's a different perspective when all of your cirques are less than 500 meters of elevation, because it's not the usual context that mountain glaciations are. And so that's why I don't call them mountain glaciers, because yes, they're mountain glaciers, but they're also on a coast. And when you have moraines at 30 meters of elevation, there are different drivers that are occurring in this circumstance.
Yeah.
Thanks, everyone. I've got to run. Some of you may know we had 110 kilometer per hour winds last night. Yeah. So I didn't get much sleep because my house was making all kinds of noises. So.
We had 97 mile per hour at my house.
Wow.
Hi, Rachel. Maybe I can ask a last question. I think great work. Would you think about the periglacial, when the cirque is exposed, right? So they have more kind of, maybe the rockfall, other things, not solely by the glacial process, can also affect the cirque morphological things.
Oh, absolutely. I mean, I do think that, I mean, this area of Scandinavia still gets heavy snowfall year round, so they are definitely impacted in this sort of periglacial sense of frost shattering and that sort of thing. And you definitely see that in some of the very steep head walls, which is why we are kind of looking for moraines that had spilled out of their normal context to avoid any sort of mass movement of glaciers. and I think it would definitely have an impact on the morphometry. But I also think that I'm working with such a large scale of repeat features that it's a sort of uniform process. So I absolutely think that the periglacial process and the evolution of the cirques impacts it. But yeah, I don't know. Getting into the question of landscape evolution too, which is I'm still trying to convince someone to tell me exactly actually how we get a cirque and how long it takes. So I ask a lot of people, so how long does it take to get a cirque? And the range of answers is incredibly large. And is it continuous? How long does it have to be a continuous? So if we can start by answering how we actually get a cirque, I think that would be a good place.
Yeah, thank you very much.
Well, I'd say you're in the right place for those kinds of discussions, Rachel. So excellent. All right.
Yeah.
Well, thanks again, everybody, for being here. Thanks to our speakers once again. Great talks, really great questions too. Really nice to end our winter series on such a high note. So thanks everybody again, and we'll be in touch in the working group one way or another.
Thanks. Thanks for the invite.
Thank you.
Thank you.
Thank you.